This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Do you have further testing setups that you're going to be going on after this one? It sounds like you've been out there a couple of times already and kind of increasing the complexity each time. What's next for this one at Lehigh?
Yeah, so we were out there last summer actually, and that was when they were building the shape table. We were working with the technicians there and Jim Rickles and Liang Cao, and we were developing sort of the capabilities that we needed for our tests. What that entails is actually we've braced off the mass that's sitting on top, and so we're using it actually to prescribe a motion across the isolation system. So this is for what's called characterization testing. So prescribed motions, X, Y, theta, to simulate some realistic event. This is mainly to understand the underlying physics of these devices, right? Okay. So we want to know, like, okay, how does that restoring force or that rolling resistance force vary with velocity or displacement or whatever? We're going to be calibrating mathematical models based on that data. But what we're most excited about with these is actually the real-time hybrid capabilities at the Lehigh facility, which they're known for. So what that means is we're going to be simulating the response of this device, one of these isolation systems, within a building. So we have a numerical model of the building that's interacting in real time, so like sub-second time scales, with a building or also with the equipment on top. So we don't have a physical cabinet in the lab, but we can model it numerically and have them interacting in real time.
So for those who may not be familiar with real-time hybrid simulation, it doesn't necessarily mean, 1 second is 1 second, but from what I understand it's real time for the particular medium that you're talking about. Can you kind of explain a little bit for those who may not know how real-time hybrid simulation works?
Sure. Yeah. And so, back in the day, before my time, hybrid, it was just hybrid testing, and you would do it actually quasi-statically. So think about if you're doing a numerical integration in structural dynamics, you have a time step that you'd be going through, and each of those you do over an extended or protracted amount of time. So you'd impose a displacement, measure a restoring force, drive that restoring force back into your numerical model, and then do another step. With the advancement of computers and the advancement of the algorithms for hybrid simulation, we actually now are real time. So all their computers run at 1024 hertz. So that's 1024 samples per second. Depending on the complexity of the model, you may not be able to run that fast. So you have to be able to solve the numerical model in the time that you need to then impose the new displacement. Gotcha. So most of ours, we've found that we can run them 5 on 1024 seconds, somewhere around there. So still very, very fast. And everything actually is happening in real time. But you just have to take a slightly longer step in your integration scheme.
Cool. So that affects, how you design your numerical model, all the equations, the level of detail that you go to, things like that.
Exactly. Yeah. And so we're modeling a 3-story building in 3 dimensions. We're using fiber-based elements. So relatively challenging elements to solve computationally in a short time step. But because of the computational power at the Lehigh facility, we're able to do this. For really complex models, so for example, they have projects where they're looking at soil structure interaction. Then you have to get into potentially machine learning or some other approach to solve really complex systems. So you have to tailor your problem and make sure that you retain enough accuracy that the problem is still realistic in a way.
Cool. So how is this scheme that your team and the Lehigh team are developing going to be valuable for future researchers or engineers or designers?
Yeah, definitely. So we've gone through this process with Lehigh, right? So we've been hand in hand throughout the process, developing that shake table, developing the protocols that we've been using for both characterization testing and the hybrid testing. So the idea now is that other users for that facility could come in and essentially plug in their system into this framework that we've developed. So whether that's characterizing isolation bearings like we're doing, or looking at some other system that's sort of at the scale that shake table is built for. We're not using it as a traditional shake table in the sense that, you prescribe a floor motion and then you let whatever is happening up top move under its own dynamics. We're constraining it in a way, but it could be used as a shake table as well. We're looking at trying to use the hybrid testing in terms of a qualification standard as well. So these bearings, if they want to be used in a data center, for example, there are certain standards they need to stand up to. So by using a hybrid test, it eliminates some of the costs associated with running large scale shake table tests, potentially.
Which are really expensive.
Yes. So very expensive. So you're capturing, for example, the building in a numerical model, and you can quickly change up what that building is.
So you
right?
go from a hospital to a data center to a parking garage.
Exactly. Which if you think about a full scale shake table test, that's challenging, right? It takes so long to build a building, and now you have that
tens of millions of dollars and months of work, as we know from our friends who are building the Tallwood project at UC San Diego right now.
But to give them credit though as well, that is, I would say, the gold standard in terms of ground truth, right? Like they actually have that specimen. We still are relying on a numerical model at the end of the day, so we have to have faith in our numerical models. So there's a lot of validation that goes in on that side.
Along with that, and this wasn't in the questions that Marty provided, but it got me thinking of brainwave here. Have you guys thought about incorporating one of your base isolation schemes on the Tallwood project as a payload project?
Yeah, so I haven't actually pursued that. I've had various ideas of actually payloading on that for other things that I work on. My PhD advisor back in the day, Henry Gavin, he actually had a payload project on one of the UCSD tables, looking at a similar system to what we're studying now. But yeah, no, I've communicated with those PIs, but I haven't actually pitched that idea yet.
If you need some grease on the skids there, let me know.
Very good, yeah.
I know they're. I think they've got the construction materials for the building at the site now, and they're working on characterization tests for the new table upgrade. They just finished. Yeah,
because I knew there was like a Tara Hutchinson, like a sort of their project they were going to do before they ran the Tallwood, right?
Yep, they're some sort of modular test bed. Yeah, basically.
Yeah, it's a modular test bed that they want to let others use. Yeah, I saw that.
Yeah, so you got a few more months until Tallwood's ready. I think they're knock on wood, going to be testing in the August-September timeframe.
Okay.
So we got a little ways, but they're definitely open for business, so to speak, for yourself, for anybody else who may be listening, of like, this sounds pretty cool to put some payload on. They're very ready and willing to work with you on that.
And what does that entail? So reaching out to the PI, getting their permission, and then submitting a proposal to NSF?
Yep. And then kind of keeping me in the loop scheduling wise, just so that we can put it on our calendar and people can see what opportunities are available for payloads on payloads, so to speak. And the NSF can see that we're doing payload projects, which they love to see. Because as you mentioned, these large-scale, gold standard, full-scale physical tests are really expensive and take a lot of time. And so we want to pack as much research and experience as we can get into them.
The most bang for your buck.
Yeah. I keep thinking, like, how cool would it be if you had a earthquake engineer, a civil engineer, and some like industrial designer work together and do a seismically isolated bar on the top floor of that, right?
Maybe we can put that as a payload project.
Yeah. Fluid delivery system, Anyway, so let your mind wander there, and if you need some help, let me know. Okay. Where can people follow along with your research as you guys are working out at Lehigh?
Yeah, so the folks at Lehigh are doing a really good job with social media. They're posting to Facebook a lot with the tests that we've done. There's a few videos available there. And then on my personal website, we have some as well, documenting the project and other projects that we have ongoing.
Awesome. We'll make sure to put those links in our show notes for anybody who's interested. And we'll make sure to point people your way. Scott, it's been great having you today. Looking forward to seeing everything that you guys are working with out at Lehigh and hopefully out at UC San Diego this summer. We'll see.
Very good. Thanks, Dan.
Thanks, Scott. Thanks for listening to today's episode of Design Safe Radio. This show is sponsored by the National Science Foundation grant number 1612144. You can subscribe to Design Safe Radio on iTunes, Stitcher, or wherever you find your podcasts. Please leave us a review so we can improve the show. Please also help others find our episodes in iTunes. Thanks for your feedback and support. You can find out more about NHERI at designsafe-ci.org, on Facebook at Design Safe Radio, or on Twitter at NHERI Design Safe.